Germany. Andreas.
Thank you, Anton. And I thank everyone for inviting us and giving me the chance to present these data from our group. This is actually ongoing studies we are conducting together with a group of the Technical University in Munich, as well as our Respiratory Research Center at the LMU in Munich. So in a previous work, we were able to demonstrate that in silico modeling of lung of a preterm infant is able to predict gas flow and volume flows, as well as oxygen distribution in this model. So this model is derived from in vivo data from a preterm infant at a corrected age of 40 weeks. And we performed lung function testing as well as lung MRI. And these data are then fed into a supercomputer, and a lung model is constructed from these data, and then by different algorithms, gas flow is simulated. So in this in silico model, we were able to demonstrate most of the previously described flow patterns during high-frequency oscillation. And in the study we are presenting here, we went further on and applied different respiratory, different ventilatory settings on the ventilator to this model derived from these two data sets, MRI and infant lung function testing. In order to do so, you need a very potent computer, and this is illustrated here. That's 144 processes working 56 days, calculating for one single breath. After that, you end up with a complex three-dimensional, and I think three-dimensional is very important, model of this infant's lung, where you can actually then put in different parameters with regard to ventilation. We did that in order to compare oxygen delivery and volume deliveries in three different settings. That's the high-frequency setting number 1 with a mean airway pressure of 8, and a high-frequency setting number 3 called here with a mean airway pressure of 12, all with 10 hertz and an oxygen concentration in the inspired air of 30%, and conventional ventilation with a tidal volume of 5 per kilograms, and the same settings here. And then we looked into the oxygen distribution within this lung model and the oxygen delivery. And here you can see the two different settings that are most distinct. That's the high-frequency setting number 3 compared to conventional ventilation. In the inspiratory limb, you can see here the amount of oxygen going into the lung and the amount coming out of the lung over time. And in the lower panel, you can see the same illustrated for 0.7 seconds on high-frequency oscillatory settings for at the mean airway pressure of 12. Here we show that the overall oxygen delivered is significantly higher in the high-frequency oscillatory settings as compared to conventional ventilation. And then if you look into the comparison of local compliances, which are indicated in blue here and normalized to 1, as compared to the oxygen delivered to the lungs, you can see that there is, despite the fact that there is more oxygen delivered, there is still a reserve in the different areas of the lung, and this in the high-frequency oscillated lung. And this can be visualized in a heat map showing the overall oxygen delivery to the lung under conventional ventilation, where you can see a reduced oxygen delivery in the left lung, especially in the mid area of this lung in the lower lobe, whereas the oxygen distribution is much more homogeneous under high-frequency oscillation in the same lung model in silico. So in conclusion, what we can show in this modeling is that the computation of data from an individual infant from an MRI as well as from infant lung function testing is applicable and can help to adopt for different ventilator settings. It can also predict oxygen distribution into the lung and enables us to change different ventilator settings and evaluate them first in silico before we go to the baby at all. So this approach actually is going to be further developed so that we don't need MRIs, which is very difficult to achieve, but that can also be derived from other image data. For example, we are hoping that we, in the end, get to the point where we can derive this lung model from 2 to 3 X-rays or even electrical impedance tomography data, and then combine those with bedside lung function testing to predict the best ventilator settings for an individual infant. So this is the whole group that was involved in this part of the study, which is our AIR cohort study, where we usually do all these measurements in each preterm infant in our unit. Thank you very much.
Thank you very much, Andreas.